idea is that you define your parameter t to be homogeneous and to be like spaced at equal intervals. And how do you imagine this? How do you picture this? You picture this essentially by imagining a flow or imagining a particular field, vector field, not to just represent the geometric position but also indicate some sort of a velocity. So now the idea is that the tangent vector or the directional derivative is the velocity of like a particular particle on that particular field. At least that is the physical interpretation. Mathematically, yes, like you can arrive at different definitions and different. I mean, there is probably much more that you can do with the idea of a tangent space, but the key point here is essentially you're equating your directional derivative to your velocity of the curve. So your directional the function that you get or the value that you get out of the directional derivative from the whole function, that is like that gives you like all your so it's like that function gives you how your velocity is supposed to vary. So in physics, what you do most of the time is it's not just velocity, but it's also other things. Like we'll just shortly see something else, but basically you just take the strong equivalence of this the equivalence that when you have a space that is somehow connected to the geometric picture of something. So you have a geometry and then you have some sort of a thing that is connected to the geometric picture but that is not geometric. So that is completely independent. So you have a kind of independent place. You define a tangent space on the curve. So it's related to the curve but it's not exactly like given by the curve per se. So when you want to do that, right, you establish a tangent basis. So what does this tangent basis do? It essentially takes your mappings of position to your velocity or momentum. And ideally, like it becomes so intuitive to understand right now because your position, like we've all been used to the way in which we convert from position to velocities. Like we learn, most of us started physics with the velocity time, distance time, and all those kind of graphs, right? So that is what is that is kind of what builds the intuition. But if you break down that graph itself, the initial graph, you should see that everything had time in it. Of course, later you do get to positions and velocities and all those kind of curves, but initially everything has time. So there is something, and something is varying with respect to time, and time is considered a homogeneous parameter. And then you have the definitions of your velocities and this and that. And velocity is basically the directional derivative along the time and the uh, distance in that curve. So the slope of that curve gives you your velocity. That is where the whole idea is coming from. But not only that, it kind of says that I'm to the space of things that I have. Say I have a n-dimensional space of things. I'm just saying that I have to have n plus one dimensional like total manifold to get, like if I have an n dimensional vector field, I have to have an n plus one dimensional manifold or a space to talk about all my to talk about certain dynamics. Okay, so now that and in fact what general relativity does is it's like it takes away the distinction between space and time, true, but it also kind of reinforces that distinction using the metric. So when you observe the metric, so the metric is essentially you have -1 -1 -1 plus 1, the Minkowski metric. So or like the other way around. So you have one of the opposite sign. So how is this coming into play? How exactly? So it's basically differentiating time in a very subtle manner, but it's also introducing a possibility of like a sense of direction which has both space and time, components of both space and time. So for example, if you have x and y, two axes, now some sort of a vector will be like a combination of x and y, and then you can rotate your basis to whatever that new vector is, right? You can rotate, keep rotating it. Now this is just a spatial rotation. Now you have a temporal and spatio-temporal rotation as well. And this idea, right, the idea of spatio-temporal rotation is what gives you your all the like and the restriction of that to Lorentz invariant quantities. That means the restriction of speed of light to be constant combined with the spatio-temporal rotation. So if you can see, it's like you can slow things down, fasten things up because of the rotation. So you can control your flow of time per se. So when you can control your flow of time, like, and it happens because of space as well, right? It's not just a pure time flow control, it's also a spatial control. So essentially you have some sort of a geometric uh, what is have a geometric warping of space time. So that is how it happens. So essentially this control, this for example your x-axis is homogeneous, and if it is homogeneous, it got to be a straight line, right? But I'm talking about in a space, in like a 2 or 3 dimensional space. So if your x-axis is homogeneous, then it's got to be a straight line. But then if your x-axis is not homogeneous, so you can just slow down your x-axis a little bit, like in the sense like separate the space, this thing, the intervals a little more. And then when you do that, you actually find out that that kind of like separation, slowing down and fastening up of the points on that axis, it corresponds to geometrically fitting the object on a curve with the shortest distance being like still the same. So basically, let's just draw this out. So essentially what happens, what I'm talking about is, for example, your x-axis is, okay, I have this, I think I have to use the squares. So it is homogeneously spaced out, right? And then when you're stretching this, say, let's just look at this, and then let's stretch it out to 2 squares or 3 squares. Okay, so now my whole thing looks like this, right, in that particular point, and then everything everywhere else. So in order to preserve the same homogeneity, what you can do is you can, all this extra distance there, that is like the extra like 2 squares that are here. Okay, so say this extra 2 squares, you can kind of tie it up around this. So this in some particular manner. So basically your new curve will look something like this. I mean, your new x-axis will look something like this. Of course, like then you, so essentially it's like you're kind of stretching something, and in order to stretch, like there has to be a curvature. So that is essentially how it happens. And anyways, coming back to spatio, like okay, the spatio-temporal rotation and all of that. So why I wanted to mention that is because this velocity. So this is even though it is kind of like even though it's kind of integrated, time is kind of integrated into space in general relativity, like it's still a mathematically tricky and touchy topic because it is still separated out from with your with the sign of your indices, and then you can actually like even do a Wick rotation to get a complexified time as we saw earlier. So we can get all of this thing. So when like you can't do those things with space, how can you do those things with time or vice versa? So there is some sort of a distinction. There is some sort of like still a parameterization. Time still is like a parameter, but it is more like holistically integrated into your studies. It's not like a stoic parameter. It's not something that is stoic, unchanging, universal. It's not something like that. But it's also very like it's given certain dynamics, but it's still like a parameter at the core. So, having said that, now the idea of the parameter of time and like the idea of the flow being established. So let's just look at one more quick example. Okay. So now let's try to find a vector field on R2n, which is the 2n dimensional Euclidean real system manifold. So with the basis or like with a collection of points given by q1 to qn and p1 to sorry, yeah. One more thing that I want to tell you, pn. Okay, one more thing that I need to bring out in this case, the moment you're seeing two bases of different indices, upper and lower indices. So as we like already saw, each coordinate or each like point, like each place in the whole what is that called? The box, the string, the
Space.
no, not that. It's a computer science term to denote a set of objects in a bracket.
Array. Array.
Array, but yeah, it's the other one. Anyways, whatever, you guys get it, yeah. So each slot in this is given by a kind of vector. The only thing is you can represent vectors two ways. Okay, actually you can this is also a really fun thing to do, right? Because what happens, so how do you, going back to the very beginning, your linear solutions, or solutions of linear equation, right? How do you do that? Say you have to like you have two variables x and y, and then you have the
Matrix.
coefficients of the variables a b c d, and then you have the answer, some number. So usually it's either 0 or is some sort of, there's some sort of constant. Okay, let's just put E F, right? So when you have this, in essence, a linear um, equation, so note that the whole idea of this, wait, is this right? Is the ABCD right?
It depends on how you're defining the equation, right?
Yeah.
You got all right.
Uh,
Right means
okay. Yeah. 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 So yeah. So anyway, so coming back, the idea is that this given, you're usually talking about your basis here, okay, and this is like some sort of like let's ignore this at the point, at this point of time. But what we can do is we can represent another system of equations, okay, that are like this, corresponding to the same space, I mean corresponding to the same solution. So instead of having vertical brackets, you can have horizontal brackets. And the rules of multiplication will be a little trickier in this case. Like, I mean, the transform, like the correspondence is a little tricky in this case. But essentially, the idea is the space of this bracket, or the rather the space of the functions that you can like operate. So what happens here is, like when you do this, right, so this doesn't become your x and y, your x and y come here, like some functions of x and y come here.
but this matrix multiplication is not possible, right?
Hmm?
This matrix multiplication is not possible, right? If you write the basis vectors as row, like like the transpose of what you have written above.
Okay, yeah, right, fair enough, yeah. Oh, I think I made a mistake, yeah. Yeah. Anyways, so the idea is, the essential idea that I'm trying to talk about is that right, when you have this as the basis, right, so this set of coefficients here becomes your dual basis.
Okay, okay.
So it the space of the coefficient becomes your dual basis. So how do you define? So you can also represent your equations, or this thing, in terms of a dual basis f a, I mean f star x, f star y. So this become the coefficients of the this thing. Okay, wait. So again, your what you're doing here, slight modification. Okay, I need to make some corrections in that. Okay, so this is not a linear equation, but it's rather a linear transformation, which is where I got a little misled. So this is the linear transformation. So what do you do when you have a linear transformation? You take x and y, and then you convert it into some other variable, right? So say, uh, give me some
X prime y prime.
L and M. So you are converting the x and y basis to L and M basis. Okay. How are you doing that? You are doing a linear transformation. So this is f of like x x f of, sorry, x to L. This is how f x changes to L, and this is f of x to M, and this is f of y to L, and this is f of y to M. So each point in that space, like each point in that matrix denotes how your x is like changing to one variable is changing to the other, right? So this system is called as the dual basis. Basically, all the functions that given any basis, you get a related basis according to that function is called the dual basis. So if x and y becomes your basis, your f becomes your dual basis. Note that the concept of dual basis is extremely confusing because of two things. One is like, I mean, I'm not even sure if it is a matrix here, but I think it is a matrix. It should be a matrix. But like, do again just check this out, because I'm just pulling the intuition off the top of my head. So anyway, with that disclaimer, the dual basis is, it gives you how the function is defined. Instead of talking about the transformation in terms of the variables, you are really talking about the function itself. Okay, so the idea here is, the idea here is that your, I don't think this is not a matrix. It's like it's it's I think this multiplication is possible, right?
Yeah,
Yeah.
it will be just a number. And on right hand side you will have a number like a function sort of. You will not have column vector.
I Okay, fine. Anyways, leaving confusions aside, so the what happens here is essentially when you talk about this, uh, this becomes your basis, this becomes your dual basis, because as you can see, your P is dependent on how your Q transforms. So your P is kind of dependent on Q. So it's also like, it's kind of like the dual of Q. It's set in a dual basis. So your velocity and momentum bases are said to be dual to your position basis. Of course, that is defined by how your position lift to your momentum, but that function, like, right, in this case, the taking of the directional derivative, right? So how that is taken is heavily determining what your P is. So but essentially, once we have established what kind of relation the basis and dual basis have, so dual bases are like vectors in the dual basis are called as the covectors. So you have normal vectors and you have covector. So when what happens is, when you like multiply these two, because of the indices, sometimes things cancel out. So for example, when you're taking the same position, same like in the sense, when you're like it when your P is given by your derivative operator, so t by dx.
Mm.
Okay, so it's like, just say, so what happens when you put x, so you get so when you get a derivative operator, right? For example, you have d by dx, and then here in q you have just x, right? So when you get this, you get 1. So
Mm.
usually, when you are multiplying, you kind of like cancel out the vectors and the covectors, and you get a unit this time. You get you get a unit matrix essentially. So that is why you kind of have that's one of the ways, interesting ways in which this is defined. But like just uh, check it out a little more, do this research. But this is the idea that I have. But anyways, moving on. Given this, just wanted to make sure that the this like distinction between vectors and covectors is not very confusing, right? It's because it is randomly propped up, and then you can see that they have like a different set of operations, and they have like when you combine both, there are certain rules. But why those certain rules exist is something to do with this link between your space and your tangent space, that or your space and your like the what is happening to that space, the transformation essentially. So this gives you some sort of like an idea of what vectors and covectors are. So it's like the space and the pure transformation. So it's like instead of transformation of the space, is space and pure transformation, which is actually a goal. Like it's like when you have a transformed space, it's basically like a space, a linear space, the initial space, and then the transformation. So with either one of them, you don't really have a complete sense of understanding. But when you put both together, you have a beautiful set of like equations or relations. So that is essentially what happens here. But
I
just
didn't understand. Like, what do you mean by pure transformations?
yeah, it's just abstract.
Like rotation is a pure transformation. Like if you take rotation matrix
Huh?
and apply it. Okay.
You could say that. You could say that. But also like yeah, exactly. The rotation matrix is a pure transformation. The this thing
I mean,
the
why are
gen
you using the word pure? Like you can just say transformations. What is the significance of the word
no
pure? Is it
when you say transformation, you automatically imagine something transforming to something else, right?
mm-hmm.
So without that something, but
Mm-hmm.
like just the essence of the transformation kept in that is why I used the word like pure transformation, just to
Like you mean like gamma zero going to gamma t, like on the curve itself it's happening. It's not going to
huh.
another space. Within the space it's
No
happening.
no
That's what.
It's rather about the notion of like it's rather about, say for example, it's like an operator essentially. The
Mm-hmm.
transformation are like operators. So they carry a set of variables to another set of variables, right? Now the very like the linearity of it all. So the
Mm-hmm.
whole idea that it is linear is one of the
Mm-hmm.
key things to keep in mind, because you are dealing with linear spaces here. But the idea of a linear transformation is basically there is, so this, if you are given some sort of a vector space basically, okay, that vector space can transform into something else, right?
Something else means like another vector space or
Hmm.
just like
Another vector space,
uh, or is it like this vector
linear,
space
yeah.
itself is rotated or something?
I mean, how do you represent another vector space? You can talk about this vector space
Yeah, you can
itself.
always represent, yeah.
Yeah, exactly.
Right.
So it doesn't really matter. But the
Mm-hmm.
idea is like exactly as you said, the rotation matrix itself. Okay,
Mm-hmm.
independently it doesn't have any value. But when you put your basis, when you input your basis, or like your initial this thing, position or like initial orientation, and then after that when you rotate it, you get the new
Mm-hmm.
thing, right? But the idea of the rotation itself
Mm-hmm.
is what I'm trying to imply by
Okay.
pure transformation.
Okay. Can you give an example which is not pure transformation?
I mean, when you talk about like everything collectively, so when you talk about something to something,
Mm-hmm.
something transforming to something, when you talk about any particular object itself transforming,
Mm-hmm.
you are exiting that abstractness, that duality. You're kind of integrating both the space and the dual space, into a system of equation or something like that. But
Okay.
yeah, so that is what, like, I didn't want to confuse this whole like system of equation with the idea of just a transformation. So that is essentially, yeah. Anyways, so moving on, we'll just try to talk about a vector field on R2n, which corresponds to this. What is the vector field that can take or that can represent this set of equation? Also, do you remember what these equations are?
I will do an equation of motion.
Yeah.
I think there should be a negative sign, right? For P dot.
Oh yeah, right. I forgot. Yeah. Anyways, so what what do you do? What is mean by a field in this point? What is the field, or like what are you exactly trying to do? So okay, note that, let's go back to our original definition of an integral curve, right? So when you say this is dq by dt is equal to dh by dp, right? And then you also have, so note that this is also setting up the whole like the duality of the basis, as I said. So this relation from q to p is kind of setting up a duality of the basis. Okay, so now and then on the other end you have p. Okay, so now what are you trying to do here? So you are trying to find the solution of this particular equation. So it's just like this is like you're splitting your say for example, instead of talking about dx by dt is equal to f of x by dou x, instead of this, instead of a direct transformation like this, so what I'm trying to do is like I'm breaking up your x, I'm breaking up your tuple, like the yes, that was the word. I'm breaking up your n tuple, like 2n tuple, by into halving it, and then I'm like mapping one, like the first element to the first element, the first element of the first half to the first element of the second half. So I'm just creating this kind of a map instead of just a direct general map of how x is changing. I'm creating instead like I'm kind of breaking x and then I'm kind of putting it together. Like it's a kind of, so it's like I'm kind of connecting x to the momentum phase here. So I'm connecting q to the momentum phase using this particular transformation. Okay, and then it's a reversible transformation. So it's not just one way, it's a reversible transformation. And the idea is I need to find out what kind of field gives me this kind of transformation. What like setup gives me this transformation, right? What is
Can you once tell the what do you mean by field? just for like revision. What do you mean by field? When you're
Exactly.
saying what kind of field uh, defines this transformation, like what do you mean by field here?
I'll give you another hint. So this is
Okay.
again. So this at this point I'm just leaving you off. Until now I've been giving like enough intuitive pumps, but I think it's a good idea if I just like um, give an equation and leave it off at that. Okay. So a very like incomplete equation too. So this is what the field is now.
This is Poisson bracket, right? Like,
Hmm?
mm, yeah. Okay, got it.
So the idea of or like exactly why this is the field is essentially you can take V and then you can put some sort of like you can put a variable, okay, and you can like when V acts on the variable it transforms to either one of these two equations. So that V is essentially Z dot, which becomes your integral curve. So if you take Q, so if you put QA here, so note that the QA terms will vanish out, okay, and then I mean the P sorry, if you took
Other term,
PA,
yeah.
then this if you take PA, then this will vanish and then you only have dou by dou PA, and then this is 1, dou PA by dou PA will be 1, and then you have just minus V is equal to Z dot is equal to minus DH by DQA. So this, and it's a pretty abstract because from suddenly from like a point of like where everything was so geometric, so linear, and like something intuitive happening. Right now you just like you're wondering what is exactly happening, and this comes from the fact, as like I told you right now, it comes from the splitting of your R2n and mapping of points like from the first half and the second half, or like mapping of the position to the momentum. So the Hamiltonian, this is the Hamiltonian system of the equation. V is called as the Hamiltonian field, and it gives you your essentially how you transform your uh, I mean, it gives you your variation. This essentially gives you your all Lagrange equation when you solve for it. Okay, but how do you get how do you get such a beautiful picture? It's something that you seriously need to like think about because it's really worth like getting um, restless about this because this is like so how do you go from um, position space to momentum space? Once you understand that relation, once you understand exactly how you go from a space of geometry to another geometric space, but that has dynamics as well. Like once you can traverse between these two things, that is when like you start seeing that geometry is not static at all. In fact, geometry gets so much more complicated, and especially the geometry of your elements of calculus gets so complicated. So when you try to split your R to n, so this is a simple fact of like splitting your R to n and kind of stitching it together.
Mm.
So, so like stitching certain points together, and it's not a direct stitching. It's like a very complicated abstract
Mm.
stitching. So from here, I think like next time we'll like look more into this, and then we'll also check out a couple of like uh, uh, couple of like cooler and more fun like more intriguing places where this whole concept of flow comes in. But flow essentially is this derivative with respect to time, and like what it does is like it is like how it tells you, it gives you a complete detailing of how you go from point A to point B. And from this understanding this whole thing, right, so you can actually even look at the least principle of least action, which is a kind of like a roundabout way, because instead of having a derivative or like a kind of like a rate of change, you have the, yeah, principle of least action. You define an action and you have a minimization principle there. So in fact, it actually minimizes like it actually parameterizes your time as well in its own beautiful way, because but it's not in using your derivative, but it's used done using your integral there. So when you look at all these things, when you try to understand like what a shape is, what a curve is, you can see that you have everything of all sorts like hidden in a curve. And then slowly, actually this one case, this one field that I showed you, the Hamiltonian field, is very beautiful because it has certain strong algebraic relations. So when you say, so what do I mean when I say I have, it has strong algebraic relation? We'll see that in a while. But essentially, like when you take all these complicated integrals and when you can remove it away, when you can wipe it off, and you just have purely algebraic constructs there. That is also something that that is that we might touch upon tomorrow, like in the next session. But yeah, let's see. So yes, I think that's it for today. Let's stop the
Okay, this
recording.
was pretty good.